Now, quick overlook of first, energy of chemical bond increases with bond order. When carbon-carbon bond has bond energy around 400, double bond will have around 600 something, and triple bond will have almost 900. Same is true for oxygen-oxygen, nitrogen-nitrogen, carbon-oxygen, carbon-nitrogen chemical bonds. Bond order also influences bond lengths. When single bonds between second period atoms, carbon-carbon, oxygen-oxygen, nitrogen-nitrogen, carbon-oxygen, are all in vicinity of 1.5 angstrom. Uh, Aromatic bond, which is between of double and single, will be 139, and then double bonds will be between 1.2 and 1.3 angstrom. Triple bond is in vicinity of 1.1, 1.2 angstrom. So higher bond order, shorter is distance between two atoms. There is very approximate correlation between bond energy and bond length. Shorter is chemical bond, higher is bond energy. The strongest bonds are the shortest. Not all atoms share electrons equally. Some of them are more positive, like alkali metals. Some of them are much more negative, uh, like halogens. When electrons in a covalent bonds are shared, the electrons are not evenly distributed, and the measure of this inequality is electronegativity. There are several scales of electronegativity, all of them giving approximately the same number between 1 and 4, or well, slightly less than 1 and maybe slightly higher than 4. The only element with electronegativity of 4 around is fluorine. Next to it, still very negative, oxygen 3.5 and nitrogen 3.1. Carbon and hydrogen have electronegativity slightly above 2. Alkali metals are all around 1. Transition metals and other metals are slightly below 2. Here is slightly different scale with fluorine exactly 4.0 and chlorine above 3 and alkali metals around 1 and below. All of scales will give hydrogen 2.1 and carbon 2.5. So hydrogen is slightly more positive than carbon, and halogens are all more negative than carbon. We do not care about these guys. If you have two atoms with different electronegativity, and this difference is very small, you have purely covalent bond. For example, it will be chemical bond between two identical atoms, like in chlorine or hydrogen. Carbon-hydrogen bond will be another example of covalent bonding. If you have difference between 0.4 and around 2, you'll have polar still covalent bond. With very large differences, you'll have pure ionic bonds. This is a very arbitrary rule, but we will not go into details in this. So when you have a polar bond, you have partial positive charge on one atom and partial negative at another atom. So in addition to covalent bond, you'll have electrostatic attraction between plus and minus. So if a bond between two different atoms is significantly greater than average of bonds between them, let's presume there is substantial ionic contribution to wave function and large difference in electronegativity between two atoms. Now let's just quickly look at it. Difference of electronegativity between hydrogen and fluorine is around 2, and we have very high energy if we compare to simply covalent bond, higher than we should expect. HCl is a smaller difference electronegativity, and this effect is less pronounced. Hydrogen and iodine have practically the same electronegativity, and we have purely covalent bond here. Just a reminder, each bond pair, two dots, is represented by one single line here. That's most common abbreviation.